This quick video will deal with rational functions, and specifically we'll be looking at their asymptotes. But the discussion of rational functions really starts with the domain. So I have here just a run-of-the-mill rational function, x plus 8 over x squared minus 9x minus 22. And the concern when we talk about rational functions really is always the denominator, right? When we have a fraction, we know that the one thing you can never have is that denominator can never be equal to 0. So in this particular instance, if we tried to solve that equation, we'd get x minus 11, x plus 2. And if we set that equal to 0, we would find that x would either equal 11 or negative 2. Now in either case, these are actually values that you cannot have in the domain because using them would create 0 in the denominator. So therefore, we have to think about what would happen on the graph. And as it turns out, on the graph, something very specific happens. So let me show you what that graph looks like. If you take a look at this graph, you'll notice that right at 11 and at negative 2, something real specific happens with the graph. And that is that on both ends, the graph itself kind of curves up and it almost like hits a wall. And the reason for that is because it runs into what we call a vertical asymptote. And so therefore, what we kind of can conclude from this is that when you deal with a rational function, vertical asymptotes will always occur wherever the domain restrictions occur. So in this case, those occur at 11 and negative 2. So this particular function has vertical asymptotes at x equals 11 and x equals negative 2. So let's continue that discussion with another example. If we take a look at this function, x squared plus 3x minus 1 over x squared minus 8x plus 15. So again, if the question we're dealing with is how do I find vertical asymptotes, I really don't need to look any further than the denominator and just setting that equal to 0. So in this case, that would be x minus 5 and x minus 3 equals 0, and therefore we have restrictions at 5 and at 3, and those would be our vertical asymptotes. Now, if you look at this particular graph, you notice that there's also a time period where the graph itself looks like it almost levels off horizontally as well. And so it is possible that some functions could have a horizontal asymptote. But let's look at what we need in order to have that happen. If you look at this graph, you can tell that right at about 2, y equals 2, right? There seems to be some type of limit to where the function can go horizontally. And that really is a function of the actual equation, the rational function itself. So let me show you the equation we're dealing with here. In this particular case, we're dealing with 2x squared minus 1 over x squared plus 4. Now let me give you some other instances of functions that would have a horizontal asymptote at 2. You could have maybe something like this, 2x to the 4th plus 3 over x to the 4th minus 7x squared plus 1. Or maybe you could have something like this, 2x plus 7, let's make that 2x to the 3rd plus 7x minus 8 over x to the 3rd minus 1. Now what we want you to notice here is that horizontal asymptotes will happen at very real specific times, and in every single one of these examples you'll notice that if we simply look at just the highest degree on the top and on the bottom, in every instance reducing those expressions would leave me with 2. And that's something to look for every time, but there are some other cases as well. So let me try and illustrate that for you for a second. Okay, horizontal asymptotes really fall into 3 categories. Number 1, the first category that we just saw. If the degree of the numerator is equal to the degree of the denominator, then the horizontal asymptote will exist, and specifically it will be the result of taking that highest degree on top and placing it over the highest degree on the bottom, resulting in something like this. So let's give you a little bit of a better example here, right? if we had 7x to the third plus 1 over 4x to the third minus 9, this particular function would have a horizontal asymptote, and the horizontal asymptote would be 7 over 4. Okay, let's look at a second case. If the degrees aren't the same, the question is, what happens? Well, if the degree of the numerator is bigger than the degree of the denominator, then very simply, there are no horizontal asymptotes. So that leaves us one other case. The only other thing that could happen is that the degree of the numerator is actually smaller than the degree of the denominator. And that would be something like, let's say, 3x plus 1 over 7x squared minus 5, right? In a case like that, the horizontal asymptote is automatically y equals 0. So that leaves us one more asymptote to talk about, and that would be what we call a slant asymptote. So let's look at the next slide. Now, if you look at this graph, you notice that in some weird ways, the graph comes down and then it almost boomerangs off diagonally. And that's because there's this imaginary line on a diagonal that is creating that effect. And that's what we call a slant asymptote. Now, if you think about the vertical asymptote, that was expressed as x equals a number, and a horizontal asymptote was expressed as y equals a number. So how would this be expressed? Well, since it is a diagonal line, this would have to be expressed in some ways as y equals mx plus b. But the question is more, how do I know that I have a slant asymptote? And if I do know that there is one, how do I find it? So here's what to look for. What we're looking for is the degree on top must be exactly one higher than the degree on the bottom. Take a look at this function. F of x equals 4x squared minus 2x plus 1 over 2x minus 3. So in this case, the degree on top is one higher than the bottom. And we know right from that there will be some type of a slant asymptote. Why? Well, because if you just divide 4x squared by 2x, you get something to the first power. And there you go. There's the part of the equation that we're looking for, y equals mx plus b. But that's not really the slant asymptote. We have to go find that. So how do I do that? Well, the easy answer is we have to divide. And I think for most people, the easiest thing to do would be synthetic division, especially in a case where the bottom is linear. So let's take a look at how we would do that. We have 4x squared minus 2x plus 1. That's going to be divided by 2x minus 3. And so more than anything else, what we need to do is try and set this up and make this easy for ourselves. So there's my divisor, 3 halves. Here are my constants. So let's see what I get. Bring down the 4. Multiply 3 halves times 4. That's 6. Bring down, add down 4. And then at this point, I don't even need to go into my remainder. You can if you want. You happen to get that. But really, this is all I need to know. At this point, I've created my linear equation, and it's y equals 4x plus 4. And that is your slant asymptote. So how do I know that this is correct? Well, take a look at the graph. There's the graph, and there's the actual slant asymptote. Fits perfectly. So hopefully this video has been helpful. Just a quick review on rational functions and all 3 types of asymptotes: vertical, horizontal, and slant.